Hello, everybody. This is going to be a quick video on matrix multiplication and how we can do it sequentially, and then sort of lead into your exercise, which would be to do it in parallel. Matrix multiplication is a sort of classic operation. It's very useful. In practice, it has all sorts of applications. And what happens here is you start with two matrices. They don't necessarily have to be squared. They are constrained in that, the rows and columns sort of have to match up, and we'll talk about that soon. But the resulting matrix is you essentially run, each individual element is sort of the multiplication of the row of one of them by the column of the other. Let's sort of dig into exactly what's happening there. So if I were to run this little visualization app I've made, you can see that there's this situation where this cell right here is going to be computed by multiplying these two together, like sort of for row 0, column 0 in the resulting matrix, we're going to multiply A00 by B00, and then we're going to add to it A01 by B10, and then we're going to multiply A02 by B20. So we're going to run the row of A and the column of B to do this one. And then this guy is, these two, you move over one column and B's column moves over. And so sort of to see through these, the rows and the columns, the rows of the A matrix determine how many rows there are in the resulting matrix. So if I bump this guy up, that will change the number of rows, in the resulting matrix. And if I bump up the columns, right, the columns of A, it doesn't change the size of the resulting matrix, but it does change how many, some multiplications and adds you're going to have to do to add it all up. And one final thing is the columns of this sort of B matrix determines the columns of the sort of resulting matrix. So there's definitely these constraints, but each individual element in this final matrix, right, is just computed by, as I said, sort of running down the row of A and the column of B and sort of adding the multiplication of each of those cells in turn. What you'll notice from a parallel perspective is there's a whole lot of reading going on over here in A and B. We're reading a ton from A and B, but we're never actually writing them, right? And there's a whole bunch of writes going on. Each individual cell of this resulting matrix, right, gets written to, and you're computing, an entire, what I in the loop I make will be K, because I'm going to go for I for each row, for J for each column, and then K is going to run down this iteration. And so there's a bunch of opportunities for parallelism here. Every single cell in this resulting matrix can be done in parallel. These operations less so, are less amenable to parallelism because they're going to be sort of each contributing their own multiplication to the total sum, and so there's sort of some reading and writing going on in the algorithm we'll see in a second. So let's just cut to the chase and start building this thing. So first of all, there's a Khan Academy example. It's very nice that goes through this example. They call them E and D, and they multiply these two matrices by each other and produce this result. And so I've used this as the example so you can sort of follow along, and just made this sequential matrix multiplier, which we're going to build right now. And so you can see, here we are in main. This is the part where I call multiply. We go into sequential matrix multiplier, and it is currently not yet implemented. So first thing we got to do is we got to do this thing where we're going to say I made a convenience method on here that says require the valid multiplication operand. So let's make sure A and B are in good shape before we even try to do anything. What this does is, first checks to make sure they're not null, and then make sure that the column count of A is, equal to the column count of B, to the row count of B. This is the constraint that we have over here, where these two have to be the same, or It just doesn't work. And so you can see when I'm, my little editor visualization here, I'm sort of locking them together. But if somebody were to call your method and these weren't the same, let's throw an illegal argument exception. And so matrices has that method there, utility method for you to call. Make sure you call it at the very beginning, just to throw the illegal argument exception in case anybody passes an inappropriate set of operands there, A and B. And so what I'm going to do is I'm going to grab a couple of things, and these go with the sort of names that matrix multiply and sort of Wikipedia and the general sort of situation of like how people refer to these is sort of usually sort of saying that A is an n by m matrix and B is an m by p matrix. And so let's get n to be the row count of A, and we'll call int m to be the column count of A. Now, this could also be called row count of B just as easily, right? They better be the same. We've just confirmed they're the same. So either one works. And finally, int P is going to be the column count of B. Now, to really quickly tunnel into these, the row count of this matrix is just the length of the matrix itself. And the column count is, well, if there's any rows at all, let's look at the 0th row and see how big that is. They better be all the same. And otherwise, if there's nothing in there, if there's no rows, then we're going to define the number of columns to be 0. This is the ternary operator, by the way. It just says for this Boolean expression, if it's true, return this guy or evaluate to this guy. And if it's false, we're evaluate to this one. And so we have these two methods. And now what I'm going to do is just start looping. And I'm going to put 3 nested loops basically together here. So I equals 0, I less than n, I plus plus, right? And that's going to be the row. Perhaps I should call it row just to make this a little bit better. I'm going to call them I, J, and K just because I've used that elsewhere. But in some ways, sort of naming this one resulting row would not be the worst idea. We're going to go from I from 0 to n, from j from 0 to j less than p here, plus j. And so this is going to be going through the cells of my output matrix. Speaking of my output matrix, maybe I should make it. And so this is going to be the result of our entire calculation. I'm going to make a new double and a new 2-dimensional double array. And like we were saying before, A is n by m, B is m by p, and the resulting matrix is going to be n by p. And perhaps the right way to think about this guy down here is to say, all right, well, this guy is really the results length. Result length. And this is going to be result sub i's length. Now they all should be the same, but sort of gets the point across of what we're doing here. Now, these can all sort of happen in parallel. This is going to be each cell in the resulting array. And so what I want you to imagine is first we could say result sub I sub j 0.0. That would sort of set it to the initial value. Now, when you create an array in Java and its type is a primitive double, it's 0 by default. So you don't have to do that at the very beginning because it is by default, but we could do that just to be explicit. Now I'm going to say for int k less than, this is going to be less than m, right? This is this matrices column count, the column count of A and the row count of B, they better be the same. And I better use k as less than m, plus k. And what I'm going to do here is I'm going to say, well, let's increment. We go back to our little thing, like imagine we're at this I and j. I'm going to go through, and as I increment k through, right, I'm going to go like sort of like I'm doing 1 sub 2, right? So like I'm going to read 1 sub 0. That's k is 0 now. Multiply these two, add them together. I'm going to go through the next iteration and just keep incrementing k from 0, 1, 2, and 3. I'll use those for the columns in A, and I'll use them for the rows in B. So I'm going to say results sub I sub j plus equals that. I'll get the old value and add the new one. A sub I sub k E sub I sub. We're all done with this whole thing. We'll just return the result. Up a little bit. Run our client and see if it produces the right result. We seem to have an index out of bounds here. Let's see what I did wrong here. Oh, I did the wrong one. So like this is a really easy mistake to make. We want to take I sub k and B k sub j. Again, and then we'll run down the little, see it's producing the correct result. If I do this like +1, that would be of course wrong. We throw an exception. Here we're sort of just checking out it is producing the correct result. And to sort of quickly go back over here to see what I'm trying to say is I was just using the same thing from both slots, right? I had a 2 by 3 array here. I forget what the exact size of this one is, but I was going off the edge of one of them and I was using the wrong thing. I was like going from here, here, and using the same spot. I need to go down the row of A and down the column of B, and I had the wrong index in there. So either way, that's a really quick demo on matrix multiply, and we'll talk a little bit in class, and you'll do an exercise on parallelizing what you can, which is, again, you can very easily parallelize all the different computations of each cell in the resulting matrix. And so with that, good luck and have fun on the assignment.